on Mars solar panels, Mars rover solar panels. After 4 years, that grant ended and they shifted focus towards lunar dust on the moon, which is what they're still doing today. Okay, so the EDS acts as a ripple wave of force emanating outward from the center, and it consists of 3 electrodes that are in a spiral configuration, as you can see here. So here, this is a cross-section. You can see the electrodes are colored. So the red one is a single electrode that's going in a spiral, and they alternate for 3. So they're given different voltages. So in between the electrodes, you can see electric fields are emanating from the positive to the negative ones. So for a positive charge, the positive to the negative, it'll experience a Lorentz force that way, and a negative charge would be on the other side feeling a force that way. So if a negative charge is with a positive charge, they'll sort of be separated until the negative charge gets put on that side. And then the voltages will shift forward. There'll be times as the particles are being pushed, and then it shifts to the next electrode gets positive every 3. And they'll just have a continuous push outward in sort of steps. There's also uncharged particles on the surface of the moon. There's 2 classes of particles. There's particles with dipoles, and there are also particles that don't have dipoles, they're just nonpolar particles. So in a uniform electric field, a polar particle will experience equal forces. It'll experience a torque, but it won't experience any force because they'll balance. There'll be equal and opposite forces on each pole of the particle. But in a non-uniform electric field, such as that of the EDS, the forces will not balance out, so it'll experience a net force. Non-polar particles have a equally distributed number of negative and positive surface charges around, and when those are exposed to an electric field, the surface charges will migrate to either end of to the poles of the particle that are defined by the orientation of the electric field that they're present in. And then this will give the particles an extrinsic dipole, which will then experience, I forgot to say it, the different forces due to a non-uniform electric field. That's called a dielectrophoretic force. So these will experience a dielectrophoretic force with the extrinsic dipole that are induced by this electric field manipulating the surface charges. So this is an equation for the dielectrophoretic force. You can see it depends on 3 different factors primarily. There's the geometric properties of the particle, so you can see that in the 4 pi and r cubed. And there's also the dielectric properties of the particle in this middle section, which is K. That K you can see there is this middle part in parentheses. So this epsilon P is the, it's the dielectric properties of the particle. It's how easily it can be given a dipole compared to the medium. Epsilon n is of the medium. So if the medium is more polarizable than the particle, then it'll experience a force inward instead of outward, because it'll change the sign on the top part of that. But since we're talking about the moon for all of this, the particle always has a higher value than the medium, so it's always going to experience an outward force, as you can see on that rightmost particle there. And finally, there's the gradient here of the electric field squared. The particle will experience a force in the direction of an increasing electric field. So if there's no changing electric field, the particle isn't going to move. So the electrodes are given only 2 values. It's just a full positive value and a full negative value, as you can see here in the square wave. And the reason this is because of how the dielectrophoretic force affects the particles. If you give them just going from positive to a negative and negative to a positive, as opposed to a more gradual change in voltage, the electric field will induce a stronger dipole in the particle before it starts to experience a dielectrophoretic force to move it. So if you had a gradual thing, it would produce a slowly increasing dipole while the particle is being moved, and overall it would just be a less effective particle transport mechanism. So timing and the spacing of the electrodes, you can assume, are all critically important to how effective the EDS is going to work. So Ben here is going to talk about how Kennedy Space Center has tested some of these different things.
Thanks, Caleb. Okay, so first off, originally the particles of 10 micrometers to 50 micrometers were placed on EDS, electronic dust shield, and a charge was given to the EDS. This is an example of the spiral dust shield, and as you can see, the dust was repelled radially to the outmost edge of the EDS pattern. Now, concerns then arose whether or not, if there was any metal in the proximity, if that would mess up or inactivate EDS. So to test this, they placed the shield on a metal plate and activated it. As shown here, it ended up working, so that was one problem solved. Another concern they had was testing it in a vacuum, especially with solar panels, which would be a big application for this. So they took 4 solar panels, 5 by 5 centimeters, and placed EDSs on them. They then had a sieve to go back and posit the particles on the solar panels on the right. Now, the particle sizes were anywhere from 0.45 to 0.67. Now, what they're looking for was if there's any effects of the spacing between the electrodes here. As you can see, each one of these black lines would be a row of electrodes, and they're wondering if the spacing between them had any effects on the dispersal. As it turns out, the 0.6 millimeters between the electrodes ended up being the most efficient. As you can see that the green line on this graph, when the dust was deposited, the solar output, which was originally 3 to 4 volts, went down greatly. And when the EDS turned on, it went back to its original voltage output. And again, being solar panels, you need to have a clear shield on them so that sunlight can still reach the panels. So this is an example of them experimenting with the translucent EDMS system. They placed, again, particles of all sizes on there. This is an example showing of particles that were 400 millimeters and above to be much, much harder to be removed by EDMS systems. And then finally, as Courtney talked about earlier, spacesuits get a lot of damage by this very abrasive dust. So while they're still in prototype, many prototypes have had successful trials where they're able to have flexibility in them so they can be applied to fabric and repel dust off of fabrics. So this could easily be applied to spacesuits. Now to tell you about kind of where this kind of testing is going, I'm going to give it to Josiah.
Good afternoon. So I'm going to do a little bit of summarizing before I begin. First of all, we want to get to the moon, but the dust is a problem. And the EDS is the solution to that problem, and we've tested the EDS here, and we know that based on our Earth-based tests, the EDS is very effective. But we don't know that it's effective on the moon, and that's what the next step is. So, our project, or the ultimate goal of this project, is to be able to test the EDS on the moon, and NASA and Pisces have given us the unique opportunity to take part in this step. So this is where we're coming in. And so, in this whole thing, we are trying to mount an EDS to a camera, hopefully on a GLXP lunar lander in the near future. When we started the design process, we came across 2 major problems. And the first of these problems was the fact that in order to run a test, or in order for any test to be successful, you have to have the ability to measure if it is successful. So in this case, we want to be able to tell how much dust is on the camera or on the EDS protection plate before and after we actually run the device. So how do we do that? The second question is, how in the world are we going to run multiple tests? You can't have an experiment that you can't run without multiple tests. It's not consistent. It doesn't show that we can get accurate results multiple times. So I'll answer the first question, and then I'll pass it off. So the first question again was, how do we test and how do we measure the effectiveness of the EDS? And so there are multiple solutions to this problem, and the first of them that we came up with was a camera light difference system, where you can see in this picture, all of these pictures that you're about to see were drawn by Amy. So I thank you again, Amy. So in this system, basically, we're taking advantage of the fact that the dust is obstructing light. The whole problem with this that we're trying to solve right now is that the dust is kicked up and it lands on top of this surface of the camera lens and you can't see through it. Well, if we use a precision camera or an accurate enough camera and we use a little bit of software, we can measure differences in light that the camera is being able to see, and then through that we'll be able to tell how much dust is on there. That's one solution. Another solution is through the use of heat. Heat capacity states that things with less mass will gain heat faster. And so we'll use this by heating the surface of the EDS protection plate, and in doing so, we could effectively heat the dust faster than the plate itself, and by taking the average heat of the surface of that plate, we can tell how much dust is on that plate. Other methods that we don't have drawn up that I will now talk about are, the first of which is weight. So, here on Earth, very accurate ways to measure small quantities are to just weigh them. So obviously we could have some sort of pressure plate on there that allow us to measure the weight of that plate, and differences in the weight amount to how much dust is on there. Other things are, we can use vibrations. So if you introduce a vibration at a certain point on the plate and you measure vibrations at other parts, the vibrations will change based on the amount of dust that's on there, and therefore we can figure out how much dust is on it based on that. And then there are other additional methods that use radioactive elements, and we use a Geiger counter, and the dust absorbs radiation and so forth. But I will have to skip to what our current hypothesis is on what would be the best for our current problem space, and that is the use of the first one that I mentioned, which is the camera light difference, simply because it is really light, doesn't take up very much space, and enables us to have a greater capacity for choosing places that we can put it on the lens. And so with that, I'll hand it off to Zach.
So we have this technology we have the EDS, and one, we need to make sure we can do multiple tests, and two, we need to find a place on a lander to put it. So obviously we're looking for some place that will get very dusty upon touchdown. So we are currently looking at somewhere on either the base plate or on one of the legs. And so the initial dusting of touchdown is not going to be a problem. We can run our tests and we have dust. But we also need to look at redusting the EDS because we need to run multiple tests. So this is a picture of the camera that we could potentially be using, and we've catted out a housing for it. So we're looking at...
So right now, the only thing that we're trying to solve right now is the ability for it to have dust on landing, because we know that is when dust will be kicked up, and we're trying to get that to be our first distribution of dust. Additionally, we're trying to figure out a way to redust it by possibly using the expulsion of gases. This right here is a CAD of the system that we're trying to incorporate onto the device, and right now we think that the best placements for that will be either on the legs or on this bottom plate over here. Afterwards, you guys can come up and look at this thing if we have time, and with that I think we're going to have to pass it on to Kyla.